Okay, so here we go. Meters. You know the basics of meters, but let's make sure we've got everything down and kind of some of the little intricacies associated with them. There are two types of meters. There's an ammeter, and if we have a simple circuit and I want to measure the current through, say, a light bulb. Here's the light bulb. Notice that I put the ammeter so that the current flows through it. It's a simple series circuit, so that means all of the current is the same. So I want to put an ammeter in series, always. One of the things I talked about in lab, if you were here, is that we have to break open the circuit to put in an ammeter. Often we talk about the current flowing through the meter. And that's kind of important because whatever flows through the meter is the same thing that flows through the light bulb. So flowing through the meter means we have to put this thing in series. Now, meters have a specified amount of resistance. So if you think about an ammeter, you don't want it to impact whatever you're measuring. So if this thing were to have a huge resistance, it would be a dam. It would eat more voltage, and it would kind of slow down the flow of current. It would completely disrupt the circuit. So one of the things we want is with resistors, we want them to be zero. And I guess I need to put the word ideally. Ideally, we would like them to be at zero resistance. That way, when you put them in the circuit, nothing crazy goes on. They don't affect the circuit, but they do still measure the current that's flowing through it. Now, the reality of the situation is if you have a cheap meter, it will have some resistance, like the ones we actually use for lab. And they factor into some of the error associated with the circuit. So ideally, we want it zero. If you're a really good meter, it has little to no impact on the actual circuit. But again, ideally, and you'll see that thrown out all the time when they have problems in the IB. The other type of meter we need to talk about is a voltmeter. And a voltmeter, if you recall, when we did our lab, we put it around whatever we were trying to measure the voltage of. It's often referred to as the voltage across, in this case, the light bulb. So we talk about the voltage across. Now you'll notice there's a node. There's another node here. So when you don't break open the circuit, we're just putting this thing in parallel. So anytime we use a voltmeter, it has to be in parallel. It has to be in parallel. And you don't break open the circuit for that. Just like the ammeter, we want to think about, okay, well, what kind of resistance should a voltmeter have? Again, you don't want it to impact the circuit. Whatever the voltage this guy has, the voltmeter is going to read, regardless of what goes on with the voltmeter. But you don't want it to impact the circuit. So if we look at this branch, current comes in, and current's going to split, and current's going to split. Well, if current splits and goes over to here, that means it's not coming to the light bulb, and that's bad. So ideally, again, here's that word, ideally, we would like the resistance to be approaching infinity. If it's a really, really big resistance here, really huge resistance, that means there's almost no current flowing to it, and all the current goes to the light bulb. So you're measuring the voltage because it's in parallel, but you're not impacting the circuit. Now, one trick that the IB likes to do is they throw in ammeters or voltmeters that aren't ideal, that have resistance values. You shouldn't get bent out of shape by these. They're just resistors in the circuit then. And it would be a resistor in series here, and it'd be a resistor in parallel, and you treat it just like you would any other resistor. So, but ideally, series, ammeters, no resistance, voltmeters, parallel, huge resistance. So that's meters, short and painful, or I should say painless. Let's look at one of the other things we talked about. We had a circuit analysis kind of game yesterday where your classmates were given this device and asked to control a light bulb. Now, one of the devices that they were given, one of the devices they were given had an electrical symbol like this. And this guy has 2 points of connection. The arrow through it merely tells you that you can vary it. Ergo the name, variable resistor. And a variable resistor is just that. It's one that you can have a dial or have a slide on it that you can make it bigger or smaller. And it has 2 points of connection. That's really important. And so if you put this into a circuit, what you're going to have is something that looks like this. Now, what happens is, it's a series circuit. So if you go through the series circuit, you can see that this is going to have a voltage drop, and this will have a voltage drop. So basically, if this was, let's say, 10 volts, some of that 10 volts will appear across this, some of the 10 volts will appear across this. Now, I can tune this resistor. So let's say first I let the resistance go to 0. Well, if that resistance goes to 0, that means it gets 0 volts, and my resistor gets 10 volts. Or if it's a light bulb, it glows really, really bright. As I tune up the resistor, and as this resistor value gets bigger and bigger, less of the 10 volts appears across here, and more of it appears across here. So ultimately, you could get, say, I don't know, let's you throw out a number, 3 volts and say 7 volts here. So you can make, if this were a light bulb, you could make it dimmer, and you could semi-control it. But the problem is you couldn't get it to go out completely, but you can let it glow fully brightness. It could get all of the 10 volts. So a variable resistor is good, and it will control the flow of current and how much voltage is being chopped up in a circuit. But you never can get what's called full scale. When we talk about full scale means you can go from 0 to, in this case, the example I said was 10 volts. You can control it completely. You can make it glow as bright as it possibly can if it's a light bulb, or you can turn it off completely. A variable resistor will not do that. It only allows you to go, say, between a moderate brightness and full brightness. So it's good, but not great. The other type of variable resistor, and it's a type of variable resistor, but it's very specific, its symbol looks like this. Oops. And it is a 3-connection device. And this has a name. It's called a potentiometer. And a potentiometer is a 3-connection device. That's really important. Those 3 connections are very important. And these symbols are in your formula booklet, in the data booklet. So it's not one you're going to have to memorize, but you're going to have to know the distinction between them. Now the cool thing about this is, literally, this takes that resistor with that 3rd connection, and it literally breaks it into a resistor to here, and then this half is also a resistor. So it's really 2 resistors together. And as you move this slide this way or this way, this resistor grows or shrinks, and this resistor grows or shrinks. So it's the same kind of idea as what a variable resistor is, but the result is very, very different. Let's show you how this works in a circuit. So if I were to hook up a potentiometer in a circuit, it would look like this. And let's say I wanted to control a light bulb. So where I'd put the light bulb is from the arrow back down to one of the other connections. Now, here's the cool thing. I said that this thing was like 2 resistors. So if you follow the current from the plus around to here, it goes through a portion of this resistor before it ever gets to, and basically what this is a node. So it's like having a resistor in series, and then it comes to a point where there's a node, and then there's another resistor here. So the current splits. Some of it goes this way, some of it goes straight through, and here's the light bulb that's around it. So basically what's happening is this portion is in parallel with the light bulb. Whatever voltage this has, this will have the same voltage. Now you may be asking yourself, how is this an advantage over what the other one did? Well, this one you have some control. So for instance, if it was dead in the middle, and let's say that this is a 10-volt battery, since there are 2 resistors and they're exactly the same, and basically the light bulb is an afterthought. These resistors are in series. This resistor would get 5, this resistor would get 5, and since the light bulb's in parallel with it, it will get 5 volts as well. So that's if it's right in the middle of the slider. But let's say, instead of being in the middle of the slider, now, it was, or sorry, of the resistor. Let's say the slider was somewhere further down, and the light bulb was still attached. Well, this is a much bigger resistor now, right? So that's going to get more voltage. Let's say it eats up to, say, 7 volts. And now, here's the node, and there's a smaller resistor here. That smaller resistor is only going to eat, say, 3 volts, which means now the light bulb gets 3 volts. So you can see as I slide further and further down, this resistor becomes smaller, this resistor becomes bigger, this one eats more voltage as a result, this one eats less voltage as a result. Ideally, and I'm going to go to the next slide so I can play this completely out, if I took the slider all the way down to here, and the light bulb's still attached, now this whole resistor is present, and this is in parallel with nothing. So that means this guy would get all 10 volts, and since there's no resistor for this to be parallel with, it gets 0 volts. That means the light bulb gets 0 volts, which means it's off. So I can completely turn off this light bulb using a potentiometer. And likewise, if the slider was completely up, you can see what it looks like. Let's say that the slider was right there, and here's the light bulb. That means it's across the entire resistor. Well, if it's in parallel with the biggest resistor, it's going to have all the voltage, 10 volts, which means this guy's going to have 10 volts. So I get full brightness here. So this is full scale. This is what we call full scale. I can go from 0 volts all the way to 10 volts. I can make the light bulb go off, or I can make it go to its maximum brightness. It's a useful device. As I told the class, way back when I was in school, we did not have power supplies. So every one of my labs had to be run from a battery. And let's say I had a 10-volt battery. So I would hook it up to a potentiometer circuit. This would be the beginning. This would be the start of every circuit that I would do. And what it does is this would allow me to vary the voltage here from 0 to 10 volts. And the rest of my circuit, whatever experiment I was doing, would be attached out here in this loop. So I could get 0 to 10 volts by moving this up and down. I didn't have a power supply, I had a battery, so I could control it even though my battery was a fixed amount. And that's really what the purpose of this is. In the IB, they're going to want you to know this, and they call the circuit that we've just been playing with a potential dividing circuit. Its purpose is real simple, what they use it for anyway. Its purpose is to generate a characteristic, running out of room, curve. You know what a characteristic curve is because you actually made them yourself. A characteristic curve is one where we plot the voltage and current for any type of device. So again, I'm just going to continue to draw this circuit so it gets ingrained in your head. So what they're looking for you to do is to draw this, and let's say I wanted to draw the characteristic curve of a light bulb. All right, I want to find the voltage and the current for the light bulb. So this would allow me to vary the voltage and vary the current in the light bulb. But obviously you have to measure the voltage and you also have to measure the current. So the other thing they're going to ask you to do, or it should be intuitive for you to do, I guess I should say, is to draw on a voltmeter that goes around the light bulb, because that's what you're trying to measure the voltage of, and also to put an ammeter in series so you can measure the current. So as you vary this up and down, you're going to change the voltage and you're going to change the current and you'll get a plot. And if this is a light bulb, it'll be a graph like this, because if you recall, it is a non-ohmic device. The resistance actually gets bigger and bigger, because remember, resistance is the ratio of voltage to current. So you'll notice this graph, the current doesn't go up nearly as fast as the voltage does. So the resistance is getting bigger, and that's one of the reasons why a light bulb glows, and it's the other reason why it burns out if you run too much current through it, because the resistance is so high you just literally burn it. But anyway, a potential dividing circuit, and its purpose is to generate what we call a characteristic curve. Make this graph. This is what it should look like every time, every time. The last thing we talked about, since we were dealing with batteries, was the reality of what batteries truly are. There were some circuits that we played with in class that look like this. They seem to have a little resistor attached to a battery, and then there was a bigger resistor, and they even labeled it as R. And if you look real close, they oftentimes had kind of a different colored box drawn around that little resistor and the battery. Because what they're trying to tell you is this is actually the battery case. And they're telling you that this little resistor inside is inside of the case. So really, when you're attaching to the battery, this is the outside of the battery. Everything else inside of the red box is inside that you can't touch. All right, so that little resistor actually has a name. Go figure. It's inside the battery, so it's called an internal resistor. And what it is, it's not really a resistor that you put inside of the battery. Nobody does that. That would be stupid. What it is, it's a result of the chemical reaction that goes on inside of the battery. The battery, remember, has some chemicals in it, and it does a redox reaction. It separates charge. It peels electrons off of one side and puts them someplace else. So that's why you have a positive side of the battery and a negative side. And it'll keep doing that, and it does that for a long time. But the problem is there are byproducts of this reaction. And over time, those byproducts build up, and that crud acts like a resistor. It prevents current from flowing. So literally, that crud is the reason why that little internal resistor is there. When you first buy a battery, this little resistor there's very little crud in there. So that means there's very little internal resistance. But as you use the battery over time, that crud builds up, that resistor gets bigger and bigger, and basically what happens is that resistor eats up everything that the battery is trying to deliver before it ever gets out. That's why a battery goes bad. This is Slode's definition of what an internal resistor is. Don't use this for the IB, but it's basically, it's a parasite. It's a parasite that feeds on voltage. Excuse me. When current flows. And that's important. Current has to be flowing for this thing to happen. So one other term that we use that we've talked about before, you often see a script E written for a battery. That script E is something called EMF, and it stands for electromotive force. It's a very old term. The way that I define it, again, this is Slode's definition. This is the ideal voltage. It's what you see on the package. If you buy a 6-volt battery, it's 6 volts. If you buy a 9-volt battery, it's 9 volt. The reality of it, it's really the maximum value of voltage that battery can deliver. So EMF is the maximum. And so if you look at what happens is, when I turn on the circuit, the battery, there's current starting to flow all around the circuit. Well, when current flows through a resistor, voltage is used. So here there's some voltage used by the parasite. So look what happens. This is what we want to push out, but unfortunately the parasite feeds a little bit. So what we end up getting is this. The EMF minus the voltage that the parasite eats is what really gets outside of the, used the wrong deal here, is really what gets outside of the battery and makes it to your calculator or whatever else you're using. This big VR right here that's actually getting to the resistor or the light bulb or your calculator has a name. It's called the terminal voltage. And it is literally the voltage that makes it out of the terminals. So if you put your voltmeter across the outside of the battery trying to see if it's good or not, you're touching the terminals. That's the terminal voltage. And it's the difference between what the battery can give and how much the parasite feeds. Now over time, as this parasite gets bigger, this value gets bigger, this value gets bigger and this value gets less. And over time, this will continue to grow and this will get less. The biggest that the voltage drop can be is as big as the EMF. So, I mean, you could literally have no volts coming out of your battery if the parasite is feeding so much. So terminal voltage is a term you need to know. EMF is a term you need to know and what it is. Obviously, internal resistance is something you need to know as well. The equation for this is sometimes written a little bit differently. It's written like so. Excuse me. It's written as the voltage that's eaten by the internal resistor and the voltage that's used outside. I'll put it that way. But we do know that voltage, by our old friend Ohm's law, is equal to I times R. So I can rewrite this equation and say I times little r plus I times big R. Remember, the circuit that I had drawn is a series circuit. So that means that the current everywhere in here is the same. So that's why I can write this expression the way I have. Oops, excuse me. So, and sometimes people carry it one step further and they say current is equal to the sum of the resistances, which is nothing new. You've done this before. Why do we have to worry about this? Because the reality of batteries is that they have internal resistance. And if we really, really, really want to do our labs justice, or we really want to talk about things happening, we need to say, look, okay, there's a resistor there. That's one other thing I used to have to do when I was in school. Not only did I have to use a potentiometer circuit, but I used to have to also measure the internal resistance of the battery so I could account for it in my laboratory work. You guys with power supplies now, there's no internal resistance. Life is pretty good. You can control the voltage and the current. You don't have to set up a potentiometer circuit. So in some instances, this is really kind of archaic physics, but it's reality. I mean, if you're driving an electric car, there's internal resistance in those batteries, and over time, you know, you're going to have an issue. You change batteries out every 4 or 5 years, and that's another $2 grand or $3 grand worth of expense. So it's, you know, antiquated, but it's not completely archaic. Okay, so here's the deal. You've now got these 4 tapes, and all the assignments have been put up online. Anything that had a worksheet to it or a PDF should be up. So as you move through this, you'll be able to hopefully take some of this, work some of the problems. There's some problems out of the book as well, and hopefully this will help y'all stay up and not fall too far behind. I can speak. All right, well, this is, for now, the last tape that will come out about circuits. There may be one more next week. So I'm going to upload these to YouTube, and hopefully you'll be able to get them offline. All right.